We're starting a new chapter. In fact, this topic on bonding is so full. It's going to take 2 chapters. So we're going to take half. We're going to more or less take it in chronological order. In other words, what theories developed first, and are they still useful? And then we'll move into the next exam will be on chapter 9. And it will expose you to the more recent theories involving bonding that are actually more powerful, but are more difficult to understand. And we'll only go into as much detail as necessary for you to be useful. Like I said before, I'm not trying to turn you into chemists. I just want to give you what you need to progress. So everything that I'm handing out, the PowerPoint slides, review document, work problems, crossword, is in Brightspace for our peanut gallery. But this is our last lab, and you'll find this in the in 103, right, on the molar mass of a volatile liquid. That's the one we're going to do next week, and that's it. That's the last lab. This is a formal report. Let's see, does it have? Yeah, it's got some questions in it. So come prepared. And this is Tuesday, Thursday. Just a reminder, Thursday I'm not going to be here. Okay, my wife's got 2 doctor's appointments that day, and one of them's in Charleston, so I've asked off for that day. And I don't think it's going to be a problem because I built in a buffer day anyhow. So next Tuesday, we'll do the review on this material. And if you want to get ahead of the game, there's already a review in there from a previous semester. So you can look at that, and I cover the same material. It's just that a review this semester, you're able to ask questions. And video, you can't ask video questions. Okay, so let's get started with bonding. These are general concepts. And the first question ought to be, what is a chemical bond? We go to basics. What do we mean by a chemical bond? It's anything that holds 2 atoms together, right? And so that they can function as a unit. And then why do atoms bond with each other to form compounds? I mean, there has to be some advantage, usually in terms of energy, an energy advantage to bonding. Otherwise, they won't bond. And we can generalize about bonding is that the energy level of, if we draw a diagram of energy here, and we have 2 elements here, X and Y, when they combine, they're going to be at a lower energy level. That lower energy means more stable. Now, that doesn't mean we can't form bonds that are higher energy. But in general, the bonds give you a lower energy state. I'm thinking in particular of nitroglycerin. Nitroglycerin, we pack a lot of energy into those bonds. But we work from lower energy substances into higher energy, but there's a dip in the middle. And that's where your compound sits. It's a lower energy than it would be up here. And that's why it's so unstable. All you need is just to look at it cross-eyed and it'll blow. And of course, the Nobel family discovered it the hard way. Alfred Nobel's brother died in a blast working with nitroglycerin, along with some other workers. So there must be an advantage to forming the bond, usually an energy advantage. And then we want to know, that's just the the beginning and the end of the story. We want to know what happens in the middle. How do atoms bond with each other to form compounds? What happens in the middle? How do they form those bonds? And we're going to talk about that too, in chronological order. Our initial understanding of what bonds were, how they form, and then we graduate eventually into chapter 9, a better explanation for bonding. Okay, we can go all the way back to Dalton's atomic theory in the beginning of the 19th century, right? Until then, chemists, well, natural philosophers, they called them. They were sort of polymaths. They just did everything. But as modern chemistry was beginning to develop, modern physics was beginning to develop, we had these laws that were being generated, and we've talked about a bunch of those. And then Dalton came along with an atomic theory to explain why these things happen. And that laid the foundation for understanding chemical reactions themselves. But it didn't offer an explanation for why the reaction occurs. It answered the why for a number of things, but not that why. And that required an understanding of the chemical bond, and that came later. We'll come back to that in just a minute. There's really no simple answer to chemical bond. And as we proceed, I hope you'll gather the difficulty in nailing down what a chemical bond is. Besides just the simple answer of it's the force that holds atoms together. And I mentioned this one already. We do know that a bond will form if the energy of the aggregate is less than the energy of the separate atoms. And if we want to anthropomorphize chemicals, we say they want to be at a lower energy. So one of the first ways to investigate chemical bonds is between ions. That's really the simplest way to approach a chemical bond. If you have a cation and an anion, then we know that there's electrostatic attraction. And physics tells us how to deal with that. So chemists are applying physics. Physicists like to say that chemistry just applied physics. And chemists like to say that biology is just applied chemistry. And mathematicians just say, you're all wrong. You're just applied math. But when we get these sodium and chloride ions close together, and we talked about the size of them, so we know that when chlorine forms an ion, it gets bigger because we're adding electrons to its valence shell, and sodium is losing electrons from its valence shell, so it shrinks. So this is a rough approximation of the size of the cation versus the size of the anion. And we can measure the distance between the nuclei. This is probably by X-ray diffraction. It's probably the most reliable way to do it. We'll talk about that next semester. But the distance between them is 1/4 of a nanometer. So they're really close. And you get this electrostatic attraction. And we can calculate the force of that, or the energy and or the force, depending on the form of the equation, the force that holds those two ions together using Coulomb's law. There's Coulomb's law. The energy involved, and that box is stuck in there again. I need to get rid of that. When you change versions of Office, sometimes it doesn't have the fonts available that you've used before, so it just sticks in a box instead. There should be a dot for a joule nanometer. So there's your constant, and then Q is the charge on one ion, and Q1 and Q2 is the charge on the other one. So you can calculate either an attractive or repulsive force, depending on the signs for those two. If they're opposite signs, then you get a negative value, and that's an indication of attraction. and then the distance between the nuclei is r. So we can calculate the energy there between those two ions. And if we do that, we find that the energy of attraction is about 10 to the minus 19th joules. So it's pretty small for those two ions. But as we know, when you spill salt on a table and look at them, you see these little cubes. Those cubes are made up of a matrix of cations and anions. And you add all those together and you get a pretty strong compound. So strong that we know we have to heat it to several hundred degrees Celsius to get it to melt. That's an indication of how strong the bonds are. Okay. So that's an ionic attraction. But we have, and we've already learned about ionic versus covalent bonds. The covalent bonds occur between two nonmetals. Right? And in those cases, you can't get a cation and an anion to attract. You have to share electrons. And so the simplest sharing that we can devise is a dihydrogen molecule. And that plate on the right-hand side represents an array of electron probabilities. Right? We don't have 1,000 electrons around the hydrogen and 1,000. It's just an indication of electron density, probabilities of finding electrons. So as they approach one another, you get an accumulation of probability for electrons between the hydrogens and a depletion of electron probabilities outside the hydrogens. And that's representative of a covalent bond between the two hydrogen atoms. Now, what we have to consider here is attractive versus repulsive forces. Because if you get, doesn't want to cooperate. If you get a proton, right, inside that hydrogen, you get a proton inside the hydrogen, you're going to get repulsions of the nuclei. And if you have electrons out here and electrons out here in the middle, you're going to get repulsion there. But you're also going to get attraction between this electron and that proton, and this electron and that proton. So it's a balancing act between attraction and repulsion as to how close can they get. They can get as close as it takes to get the lowest possible energy in balance of the repulsion versus attraction. Okay, and here's a representation of what that looks like in a graph. The best way to look at this graph and interpret it is to start at the right-hand side, not the left. The right-hand side is where you have two separate hydrogen atoms. And their potential energy, and this is a relative value. We're saying it's 0 when they're far apart. Okay? As they get closer, you see that the potential energy tends to drop. And as they form the bond, the minimum potential energy, which is the most stable situation, occurs when they're 0.07 nanometers apart. Right? If you try to push them any closer, then the repulsive forces start to mount up as you get those protons closer to each other. And that's why the energy goes way up as you push them close together. So their preferred distance is this 0.074 nanometers. And the bond energy is given as minus 458 kilojoules per mole. Okay, so it's a reasonably strong bond. The other thing that we can learn from this graph, which doesn't have anything to do with chemistry, but has to do with nuclear power, is how do you get those nuclei to fuse? The sun does it, right, because it's so big, and it has forces of gravity that concentrate these hydrogens together, and then the pressure from above keeps them close together until you get close enough so the nuclei experience a new attractive force, the strong nuclear charge. Once they get that strong nuclear involved, then they bond and you get helium. and they give up energy. But on the way there, it takes a lot of energy to get them that close together. Okay, so chemistry doesn't deal with that, right? We don't have the technology or the desire, for that matter, to deal with it. In chemistry, our measuring accuracy is such that when a reaction occurs, if it's exothermic, it gives up energy. Where did that energy come from? Well, a physicist will tell you that you converted some mass into energy, and that's true. But it's so small energy, the mass is even smaller, right? We can't even measure it at our level. So what we say in chemical terms is the energy in equals the energy out. So there's a balance there that we can't measure fine enough to invoke nuclear reaction. And that's the hydrogen bond. Okay. So as a review, ionic bonding requires complete formation of a cation and an anion, at least. And then you can get that electrostatic attraction. And that occurs between metals and nonmetals. Okay. Electrons must be transferred. Covalent bonding, of course, is sharing of electrons between the two nuclei. And that occurs between two nonmetals. Now, there's another type of bond that we'll allude to later, the metallic bond, where you get two metals bound together. Okay. Here's a very important point. Like I said before, nature just does what it does, and we try to make sense of it. One of the ways is we classify bonds into ionic or covalent. The reality is that these bonds are on a continuum, and all but a very few bonds have some character of covalent to them and some character of ionic to them. Now, of course, the farther apart they are on the periodic table, the more ionic they are, like sodium and fluorine would be extremely ionic, very little covalent character. But if you took, say, iron and oxygen, they would have a little more covalent character to them than the sodium and fluorine. Now, when we got a covalent bond, the nature of the covalent bond can be slightly polar. What do we mean by polar? Well, if we say, let me see, I want to use a phrase, hydrogen and fluorine. Right? We've studied electron affinity. Right? So we know that fluorine has a very high electron affinity. Hydrogen is a much lower electron affinity. Right? We look at periodic table or periodic trends. Right? Electron affinity means that the electrons are more strongly attracted to fluorine than they are to hydrogen. So this gives you the potential for, and actually the measured polarity of that bond. So the electrons may be polar. I mean, they may be covalent. The bond may be covalent, but the electrons tend to spend more time closer to the fluorine because of its stronger attraction. But it's still a covalent bond. So we represent that in a couple of ways. We say not a full charge, but a slight charge is attributed to fluorine, and a slight positive charge is attributed to hydrogen. That's what that little delta means, slight. And the other way to do it is say if the bond is polar, we're going to put an arrow here saying that's the directions the electrons drift, and it leaves a slightly positive behind. So there are two ways to represent it. Now, if we're talking about a nonpolar covalent bond, the only way to get a perfectly nonpolar, is to bond two of the same elements together. So like hydrogen. That'd be nonpolar for sure. Or nitrogen. That would be nonpolar. because the attraction from either side is the same. Equal sharing of electrons between the atoms. There's no charge separation at all for those. Polar covalent bonds, and now we're still on a continuum. I was talking about a continuum between ionic and covalent. Now within that covalent, you can either have non-polar, or you can have slightly polar or more polar. So it's a continuous range of possibilities. Polar covalent bonds have unequal sharing of electrons, and this is a perfect example of a polar covalent bond between hydrogen and fluorine. Now, if it were a gas, it'd be hydrogen fluoride. Right? If it were dissolved in water, it would be hydrofluoric acid. Okay. And we can measure that difference. Right? We understand the charge separation between those two plates, and we can arrange it so, and we can adjust. Actually, we get a plot of changing capacitance between those two plates, and then we watch how that capacitance changes when we have hydrogen fluoride in between. And this would be, they'd have to be a gas. Okay, and from that plot, you can pick out either a dip or a peak or something in there that tells you this is where all the hydrogen fluorides are perfectly aligned. And that, measuring the charge difference between those plates, will tell you how strong the polarity is for that molecule. And measuring the polarity of that molecule also is the polarity of the bond, because there's only one bond. Okay? If you try to do that with more complicated molecules, all you're going to get is a composite of the bonds in the molecule, like water would have two of them. But since they're both equal, then probably you cut it in half and you'd be pretty safe. Okay. What's meant by a chemical bond? Well, in general, it's the force that holds atoms together, or groups of atoms together, to function as a unit. Why do atoms bond? Well, the simplest explanation is because separated, they have a certain energy level. Together, they have a lower energy level, which is more stable. How do they do it? Well, they do it at this point in our discussion. They either bond as ions or they share electrons. Ionic bond versus covalent bond. Okay. Now that concept I mentioned here, where we're using electron affinity as our discussion topic, there's a simpler way to deal with it. And it was first proposed by Berzelius, who was a Swedish chemist. And this was in the beginning of the 19th century. He wanted to discuss these differences in attraction for electrons in terms that he called electronegativity. So the more electronegative an atom is, the stronger its attraction. And there are several methods for developing a system of numbers that we can assign to each of the elements. But the one we use most often was proposed by Linus Pauling. Linus Pauling was a chemist. He was a biochemist. And he was, to say the least, brilliant. In fact, Linus Pauling wrote a book called The Nature of the Chemical Bond. I think I've got it part of the slide here. And he drew everything that it was known at the time, from the beginning of the 20th century. Everything we knew about the chemical bond at that time, and put it into a manuscript, and tried to, and wove a coherent story about the bond. And it was so widely accepted, and and was so useful that he got a Nobel Prize for it. But he also proposed this scale for quantifying the electronegativity of elements. And as usual, you can do your work, like in this case, in the 20s and 30s, and it takes the Nobel Prize Committee about 20 to 30 years to catch up and say, okay, so you had a good idea and we'll give you a prize for it. By that time, you're probably retired. So this, let's see. Oh, that's an interesting fact. He got a Nobel Prize in chemistry for his description of the chemical bond, but he also got a second one a few years later for his work, his activities on behalf of nuclear nonproliferation. So he got 2 Nobel Prizes, one in chemistry and one for peace. He actually did something to earn the Peace Prize there, not like Obama. Obama's only reason for getting a Peace Prize was he was the right color. Okay. So we're going to, when we talk about electronegativity, we're going to be using numbers that were created by Pauling. So, and you can look up periodic tables that have these numbers along with the element symbols. They have a number in here that gives the electronegativity. And this is how he calculated it. The expected bond energy between 2 atoms. Here we're doing hydrogen and some other element. But it could be 2 different, it could be 2 other elements, doesn't matter. And then we take the actual bond energies measured for the individual atoms bonded to themselves. Add those together and divide by 2. That's the expected energy for the bond between those 2 elements. So that's only the first step. This is the expected bond energy, and then we measure the bond energy for those 2 elements and compare the difference between those 2. The actual minus the expected gives us a value. And that's what Pauling is reporting as electronegativities. If the delta is 0, then you have a perfectly nonpolar bond. Okay. Yeah, we're coming up. We're going to see a periodic table in just a second. As a trend, the electronegativities, this one. There's our periodic table. We come over here, transitions, and then the alkaline metal and alkaline earths. And the trend for electronegativities that I'll abbreviate EN is from lower left to upper right, increase. And we leave the noble gases out of this because they don't want electrons anyway. And the lowest one that's calculated is on this lower end for cesium or francium. I think cesium and francium are both the same at 0.7. And fluorine is 4.0. So it has the highest electronegativity, as we would expect, based upon its electron affinity measurements. This system is a little easier to deal with because electron affinities are in measures of joules per mole, and they can be some wild scientific notation. It's kind of like, well, we haven't got to it yet. I'll have to save that for next semester. But simplifying the situation with this numbering system makes it easier to deal with questions that are asked about certain bonds. Okay, here we have, excuse me. Here we have the periodic table, and we see that lower left, cesium and francium are the same, upper right, fluorine. And if we go up in a group, we increase. If we go from left to right, we increase, as long as we're representative elements. Once you get into the transition elements, then you're in kind of a roller coaster. Okay. And there are valid reasons for that. But as a general trend, lower left, upper right is increasing electronegativity. Okay. So if we take lithium and fluorine, which has more attraction for the electron? Well, lithium's over here and fluorine's over there. So fluorine should have the greater attraction. Right? If we have fluorine and iodine, so iodine's down here, right? Then fluorine should have a greater attraction for electrons. Oh, why? Well, we go back to electron affinity. Right? The greater attraction for electrons, for electron affinity, will give up more energy as the electron settles into its outermost orbit for the atom. So as we get more negative with the electron affinity, we get higher in electronegativity. And that's because from left to right, increasing nuclear charge. You have more protons pulling on those electrons. Here is this trend up and down. We decrease the electronegativity from top to bottom because we're adding orbitals. And when we're doing that, we're adding those electrons in close to the nucleus, which is shielding the nucleus. And the outermost electrons don't feel the full force of that increased nuclear charge. So combined, we get lower left to upper right increase. All right. So the lower left to upper right, explain the trends across the period, increased nuclear charge, down a group, more shielding. So there it is in black and white and blue and red. Okay, now when we talk about the polarity of bonds, this is sort of a, I don't know, a rule of thumb or useful trends. If you take the values here and you subtract the lower one from the upper one, from the higher one. So in this case, if we took cesium and we said, all right, we're going to form a compound between cesium and fluorine. So we take 4 and minus 0.7. That would be 3.3, would be the difference. That's a huge number. This is definitely a polar bond. It's an ionic bond, actually. So the ionic bonds are anything greater than or equal to 1.5 difference in electronegativities. Anything less than that is covalent. So less than 1.5, which would be 1.4 or below, would be covalent. So we also want to subdivide the covalent into nonpolar and polar. Well, if it's between 0.3 to 1.4, we have a polar covalent bond. And that's in the case of nonmetals. You have two nonmetals, and this is the difference between their electronegativities. You have polar. Anything less than 0.3 is considered nonpolar. Okay. The caveat is that if these are nonmetals, that's true. But if you have a metal and a nonmetal, and it's in this range, then it's more than likely ionic anyway, or has more ionic character than it does covalent character. So that's kind of a gray area. Okay, most to least polar. All right, the first one, A, is fortunate because every other atom is bound to a fluorine. So we get this one, we get oxygen and carbon. Okay. So we know the fluorine is going to be 4. All we have to do is look at their position in the periodic table, right? Carbon's over here, then nitrogen, then oxygen. So the least, most to least polar. So the least polar is going to be oxygen and fluorine, right? And the most polar is going to be nitrogen. So that means carbon and fluorine. Oops, sorry. My mistake. Carbon and fluorine is the most polar, and then nitrogen would be in the middle, based upon their position in the periodic table. Carbon, nitrogen, oxygen. Okay. For the second one, we have a mix. So we have carbon and fluorine, we have nitrogen and oxygen, and silicon and fluorine. So if we're going from greatest to least, the ones that are furthest apart from each other in the periodic table. So let's see, we've got nitrogen, oxygen, carbon, fluorine, silicon. Where's silicon? It's under carbon. The silicon's here. Silicon to fluorine is the greatest distance, so it's going to be the most polar. And then the next would be carbon and fluorine. And the least would be nitrogen and oxygen because they're right next door to each other. So silicon, carbon, nitrogen. Okay. Let's see. I'll leave that here. We might want to refer to it later. The third one. Has 2 chlorines. Right? We know that's nonpolar. Let's see, boron and chlorine and sulfur. Right? So the least is going to be chlorine and chlorine. Then we need to say where's boron and chlorine relative to chlorine. But boron is way over here. Chlorine is down here. So that's probably the greatest distance. Boron, chlorine would be here, and then sulfur and chlorine would be in the middle. The sulfur is a calcogen, right next door to chlorine. Boron, sulfur, chlorine. Yep. Okay. So let's take another one. Which of the following bonds would be the least polar yet still be considered polar covalent? All right, so what do we have to deal with? Magnesium, oxygen, carbon, oxygen, silicon, oxygen, and nitrogen. Okay. Let's read the question backwards. Still be considered covalent. And then polar covalent. So which one would not be covalent? Metal and non-metal. Got any more? No. Okay, so now polar covalent. Are there any that are non-polar? Yep. Throw it out. To answer the question, now we can go least polar. So the least polar would be where the atoms are closest together. Carbon and oxygen separated by 1, nitrogen and oxygen next door neighbors. That would be my choice for the least polar yet covalent. Okay, let's take that same set and say now most polar without being ionic. Okay, so we can throw that one out. We don't have to throw this one out, but it's not polar. Well, I guess we do have to throw it out. Most polar without being ionic. So we throw those out. Most polar would be furthest separation. Right? So it's not this one anymore. It would be the ones farthest apart, silicon and oxygen. Oops, why did I say? Oh, we're actually given numbers. Right. So we can do the calculation. So carbon and oxygen would be, let's see, 2.5 and 3.5. So that's a difference of 1.0. How about silicon and oxygen? 1.8 and 3.5 and 1.8. Okay, we're faced with a technicality here. That one would be considered ionic. Okay, so I got caught in my own, hoisted on my own petard. So yeah, if it's still covalent, then carbon and oxygen would work. Now, if I didn't have those values to go by, it would be difficult to answer that question. Okay. So we're going to borrow a concept from physics. It's called the moment. The moment is an expression, is a vector value for force. So now vector, well, I'm just assuming you've never heard of it before. A vector has two components in it. It has a magnitude and a direction. Best way to learn the difference is speed is magnitude only, like 70 miles an hour. Going this way, that way, that way, that way, doesn't matter. But a direction would be 70 miles an hour due east. Okay, that's a vector. Okay, so when we talk about moments, dipole moments, we know what the dipole is between two unequal atoms. The moment says it happens between those atoms, and it can also be combined with other moments in the molecule to give you an overall dipole moment, okay, a composite. That's where we're headed. And that's where that arrow comes in. When I gave you that arrow with a plus sign on it, that's a representation of a dipole moment because it has direction to it. Now, of course, the size of the arrow can indicate the magnitude, right? But definitely the direction is the arrow. Okay. That's what we use to indicate a dipole moment. So when we have a molecule, for instance, like water, we've done the Lewis dot structure for water, correct? Yeah, okay. It's going to be a bent molecule, right? It's going to have two lone pairs of electrons. And each one of these bonds is going to have a dipole moment. It's going to be toward oxygen. Oxygen is more electronegative than hydrogen. Okay? But that molecule can be described in terms of a composite dipole moment. And in a vector addition has to take into account direction. So if you have two dipole moments like this that are equal in magnitude and opposite in direction, they cancel each other out. So the overall dipole for the molecule would be 0. But if they're at an angle to each other, then you have you can do a vector addition. The best explanation for that is when you take physics, the first thing you learn after all the basic history and stuff is statics. These are forces that are opposing or compiled, but there's nothing moving, right? It's static forces. So if we have two forces being applied here, one is in this direction with that magnitude, and one in this direction with that magnitude, you want to know what direction and what is the magnitude of the force that this object at that point would actually feel. And what you do is you draw a parallelogram equal in length and parallel to that one. It's about right, something like that. And then parallel with this one, and the composite goes from here to here, right? So this is the vector addition, the sum, vector sum of those two. And you can do the same thing for the dipole moments of a molecule. So when we add these together, right, you're going to get an overall dipole like that. Okay. Now, I danced around that barn several times in order to make this point. When you're determining the dipole, overall dipole of a molecule, you need to know two things. One, do the bonds, do they have a dipole moment? So you need to know dipole bonds. And the second thing you need to know is geometry. How do those dipoles add together as vectors to give you an overall? So if they're equal and opposite, either facing each other or go in the opposite direction, they cancel out. And that gives you a 0 overall. But if they're at an angle to one another, then the geometry tells you that there will be a vector summation and you'll have a net dipole moment for that molecule. If we did carbon dioxide, we drew carbon dioxide before, I'm sure. Right, you got a dipole this way, dipole that way, and they cancel out. Carbon dioxide has no dipole moment for the whole molecule. Now, you still have uneven distribution of electron density either side. But with a small molecule like this, it's likely not to have a significant impact. And in fact, we used to use carbon dioxide in its supercritical phase to extract organic compounds from plant tissue. So we pressurized it and cooled it enough where it was in the, actually you didn't cool it. We pressurized it until it went into the, we've talked about phase diagrams, haven't we? Or is that second semester? Second semester, sorry. But we use supercritical. It's a supercritical fluid. And you can use that because it's nonpolar. It will penetrate those cells of the plant matter and extract organic molecules without damaging because the temperature is not high enough. Rather than a methanol reflux. That's neither here nor there. But methanol reflux is very hot and it cycles and you gather the extract in the container where you're boiling it. So you have heat damage for some of your metabolites. Well, with this method, you can extract them and they're just as pristine as they were inside the cell. And to get your extractant back, all you have to do is release the pressure, the stuff blows off, and you're left with your extract. But it's all due to the fact, well, one of the facts is this is a nonpolar molecule. And that allows it to very easily, and it's a small molecule, penetrate the cell and do its thing. Okay, You need bond polarities and geometry to know. And here's the water molecule. All right, so you see representation of the dipole moment, the composite dipole moment in the center, and then an artist's idea of what the electron density would look like. Red means more electron probabilities, blue means less. So it's slightly positive on this side, slightly negative on that side, and that gives you your dipole moment. There's carbon dioxide, and that's not drawn correctly because carbon and oxygen have double bonds between them. Okay. And here's examples of some other molecular geometries. We have the linear in the top one. Carbon dioxide is a good example of that one. The second one is trigonal planar. So you can have linear. Let me remove this. These are not all the geometries, but they're the most common and the easiest to reason with. So you can have linear geometry in a molecule. You can have trigonal planar, which is another way of isosceles triangle. Right? And that's the outline. That's the outline of the molecule. Like if you connect all the B's with lines, that's your trigonal planar. But the bonds themselves actually occur between that central atom and the atoms at the apex of the triangle. Okay, so it's important not to get those two confused. We see the geometry of the molecule is this, but don't forget that there's bonds holding it together. There are bonds holding it together. The next one would be tetrahedral. And these are regular geometric shapes. So if you have a central atom and then 4 equally spaced atoms, then you would have a tetrahedral shape. It's a triangular base pyramid. Okay. There are more, but I don't want to introduce you to them yet. Let's talk about what forms a stable compound. Right? We talked about the energy balance that promotes the formation of bonds. One concept that's useful is the octet. Now, the actual discussion of the octet can be simple or complicated. We're going to use the simple version. And we're going to anthropomorphize atoms to do it. These atoms here, anywhere else, these, let's see. Let's say we've got a column here with our noble gases. Right? So we got helium here, and then, then neon, and then argon. Let's see, that's neon, argon, krypton. Krypton and xenon. These all have complete outer shells. They have full octets. Everybody else in this periodic table is trying to electronically look like a noble gas because they are the most stable. So what would it take to make an octet for fluorine? Just 1 electron added. Oxygen would take 2 electrons. Nitrogen would take 3. Carbon would take 4. Or carbon could lose 4 and go this direction. Or it can add 4 and go this direction. That's carbons. Maybe that's why we're carbon-based life forms, because they're so flexible. So the octet is where, especially for the second and third period, the octet rule works very well. We're trying to form that octet where you have S's and p orbitals full. Right, 2 for the S and 6 for the P's. When you get to period 4, down here, now you've introduced d orbitals. And then you can deviate from the octet rule. Okay, and then we're going to look at some examples of that. So did we talk when we did electron configurations? I think I talked about 10 and why the predominant ions for 10 were 2+ and 4+. We talked about that, didn't we? Right, 10 is over here. So it has 2 s electrons and it has 2 p electrons. So if it loses the highest energy ones, the highest valence electrons would be 2 p's. If it loses the 2 p's, now it's a 2+ ion. If it loses those plus the 2 s's, and they're in the same energy, in the same fifth period, if it loses those 2, now it's a 4+ ion. So that's our explanation for if it loses all 4, then it's got an octet and it looks like krypton. But if it loses 2, it's going to look like strontium. Lead would be similar, except lead's in a different period. It's in the 6th period, but for the same reasons. Bismuth is moved over 1 next to lead, so it either loses 3 and makes 3+ ion, or loses 2 more s's and makes a 5+ ion. Thallium, where's Tl? Next to lead. If it loses 1, it's got a full s orbital. If it loses those s's, now it has a 3+. So those are the predominant ions for those elements based upon that reasoning. Let's see. Isoelectronic series. See, we did do when we talked about, atomic structure. Okay. Sometimes I get confused because of too many courses going on at one time. Let's see. Let's make a little room here. And I guess I'll have to leave that there. So I won't have to write it again. But what is an isoelectronic series? I feel like we talked about this before. An isoelectronic series is simply a series of atoms and ions that have exactly the same electronic structure, right? All the s's and p's and d's, same structure, same number of electrons. Now, they're obviously going to have a different number of protons because they're different elements. But if we remove a certain number of electrons so that they all, from each one, so that they all have the same electronic structure, that's an isoelectronic series. So oxygen 2-, fluorine -, neon, sodium, magnesium 2+, aluminum 3+, they all have the same electronic series, electronic structure, which would be the neon structure. And that's a complete octet. That explains why at the very beginning of the course, I had you learn that +1, +2, +3, -1, -2, -3. That's why. Right? That when you were naming compounds, you just had to learn those things. But this is why it actually works. And that begs the question, why didn't we start here? And then name compounds? Then it might make more sense. And there's some courses at some colleges that do it that way. Okay. Choose an alkaline metal, an alkaline earth, a noble gas, and a halogen. So that they constitute an isoelectronic series when the metals and halogens are written as their most stable ions. Okay. We could go to, say, krypton, right? Halogen would be, let's see, put krypton in the middle. And then we have a halogen, let's see, it's an add one, add one electron, bromine there. And then we go back and say calcium with a 2+, and potassium with a 1+. Those should be isoelectronic. Oh, wait a minute. Oh, that's argon. I moved, my mistake. When you take an electron away from potassium, now it looks like argon, not like krypton. And then chlorine would have to be one electron added. So that's that is one correct series. If I made it krypton, then I'd have to use rubidium and strontium here. Then I could use bromine. That would also work. Now, for this one given, the electronic configuration is that, where we have 3s2 and 3p6. That would probably work better, because when you get down here, no, that works. Yeah, that works fine. Because we're not introducing d orbitals at all. Number of electrons for each species is exactly the same, 18. And there's your number of electrons. Same as protons. But the number of protons is going to be different for each one. It has to be. Otherwise, you got different elements. Okay. We've looked at, in the previous chapters, we looked at atomic size. We had some problems that we solved for ionic radius, but we didn't really go into it in deep detail. Ionization energy, yes. We know the trends there. We know electron affinity, which was left out of this sequence. And now we know electronegativity as a trend. We've talked about electron configurations, okay, and isoelectronic series. We can predict formulas for ionic compounds. All we have to do is balance the charges. Right? So calcium and chlorine would be 1 calcium and 2 chlorines, because we'd have to balance a 2+ for the calcium and 1- for the chlorines. We've ranked bonds based upon their differences in electronegativities. So we can devise a covalent bond polarity scheme based upon these general rules. Okay, what are the factors that influence the stability and structure of solid binary ionic compounds? When we say binary ionic compounds, we're talking about a cation and an anion, or like this, or what else? Maybe this, aluminum fluoride. Those would be all binary, right? Cation, anion, ionic compounds. There's a concept that describes the strength of the bond called lattice energy. What is it that attracts these ions together? Now earlier we talked about coulombic forces, right? We calculate for individual ions. But as a practical matter, when we're talking about the strength of the ionic crystal with all those cations and all those anions together, the lattice energy is more useful value. So we need to define what a lattice energy is. In order to define lattice energy, and when they say lattice, they're talking about the crystal lattice, where you have cations and anions and anions and anions and then cations, and that whole array of positive and negative charges. That's the lattice. And next semester we'll talk about the geometry of those lattices. But this lattice energy is defined in terms of so that we can eliminate all other extraneous forces. The ions must be in gaseous state. So let's use sodium chloride, for instance. We'd have a sodium ion in its gaseous state combined with a chloride ion in its gaseous state, and it produces a solid. That energy is the lattice energy. Now, is it going to be a negative sign or a positive sign? Negative. It's exothermic, right? This is more stable than that, so it gives up energy. And by our convention, that's a negative number. Okay? It's exothermic. It's extremely exothermic. Now, calculating this value, we can also use some proportionality constant K, and it probably varies with the cations and anions. So it's a little, you'd have to look it up. Then you need the charge on each one and the distance between them. Okay, so this lattice energy is dependent on the strength of the charges between the cations and anions and the distance between them. So since R is in the denominator, if the distance is small, the lattice energy goes up. As they get closer, the lattice energy goes up. And if the Q's are large, say instead of positive and a negative, say we have 3 positive and these 3 negatives, so we have a 3 plus and these negatives, those values also add to the strength of the bond. Or actually, it would be better to do, say, this one. Oops, not that one. Calcium oxide. So this is 2 plus and this is a 2 minus. So the Q1 times the Q2 would be greater for this one than it would be for this one because of the size of the charges. And then it depends on how close they can get to each other. Okay. So now that we know what the lattice energy is defined as, we want to use what we know to actually quantify the energy of formation of a compound. So you remember what we talked about, energy, the formation, the energy of formation. We have a compound, we put it, let's see, we put it here. So let's say sodium fluoride in its most stable form is a solid. Okay. And in order to do the formation for that, we have to leave that alone. That's 1 mole. And we have to say, okay, we're going to make it out of sodium in its most stable form, solid. And fluorine in its most stable form, diatomic gas. So we only need 1/2 of it. So that would be your formula for the energy of formation. That's overall. We can break that down into separate steps. Set of steps for this part, set of steps for this part to give us that. Okay, and that's what we're doing here. First of all, you have to get the metal into a gaseous state. So we would take sodium solid and we would make a gas out of it. And this would be endothermic. So the delta H would be positive. You'd have to put energy in to get it there, right? Okay. Now, once you've got it in this gaseous state, we want to ionize it. So this would be called the sublimation energy, right? Because it's going from a solid to a gas. And then we would take the gas and we would add more energy and ionize it. Right? Y'all recognize that as ionization energy. Actually, the first ionization energy. Okay. Now we've got that sodium in this gaseous state right here. Okay, so it's ready to go. Now we would take the fluorine which is, excuse me, it's iron. We take the fluorine, half those fluorines, and we would, it's already gaseous. So now all we have to do is dissociate. So now we get this fluorine atom like that. Okay. And this is dissociation. All we had to do was break the bond of that gas. Okay. Then we take that gas. Why do I keep doing that? And we allow an electron. So this is electron affinity. It's going to give up energy. Oh, this is endothermic also. Oh, we're on to the next slide. Sorry. So now we allow an electron to fall into this fluorine and give us this fluorine ion. And this one is exothermic because that electron is coming from infinity and it falls down to the outermost orbital. So this is electron affinity. Okay. And then the last step is to take this one, and let's see, sodium gas plus fluorine ion gas yields sodium chloride solid. And this is extremely exothermic. And this is the lattice energy. Okay. So we went from this solid, this gas, to this solid in those steps. So we took this overall and broke it into its pieces. And this is what it would look like on the energy diagram. These are two reactions. There's one on the left and one on the right. So they're not combined. It's just a representation of two different forms. We're forming magnesium oxide on the left, and we're forming sodium fluoride on the right. And we take those steps and we plug those in there. Right? We add energy, get energy back. Then the overall is the same as if we went from here to here. This process will give you the exact same energy. But it shows how each step is accomplished. Now, in nature, all this is happening at once, right? But this is how we rationalize it, how we quantify it. It's not that we can't measure each one of these steps, and we do. Right? So here we have an example of lithium and fluorine coming together, lithium fluoride, and we're going through these same steps. We do sublimation, then we do ionization energy, and then we do dissociation with a certain value. Then we do the formation of the electron affinity, right? We get energy back. There's a negative value there. And then we do lattice energy. We get a whole lot of energy back. And each one of those steps, we combine those values, we end up with minus 617 kilojoules overall for lithium and fluorine. Okay. Now, why are we going to all this trouble? Well, sometimes we want to find out if we compare this one with some other one, which one has the stronger affinity for fill in the blank. Sometimes you have to look at individual steps to see which one has the stronger affinity. In order to do that, you've got to do a calculation and figure out what that value is. Okay. Some of the individual parts is we've already done that. We did that on the chart. And I think there are example problems in there, working just this type of problem and getting at individual steps. When you know the overall and you know some of the steps, then you can get at the individuals. All right. We mentioned earlier that covalent bonds, nearly all of them have some ionic character. That statement, no bonds reach 100% ionic character. Well, that's true. They always have some covalent character because there's going to be a little bit of overlap, especially when the ions get close to each other. You're going to have some overlap. So you get some covalent character in what we'd normally consider 100% ionic. And the percent ionic character can be calculated if we measure the dipole moment for the covalent bond and divide it by the dipole moment for the ionic bond between those two atoms, and do the ratio times 100, and that'll give you an indication of their ionic character. We do get 100% covalent character. I mentioned that earlier. If the atoms are both same element, then you don't have any choice. I mean, they're 100% covalent by definition. But notice that the percent ionic character for these hydrides in the bottom they're very low, but the electronegativity differences are very low also. So that's a good indicator. And then when you get the electronegativity differences very high, then you move into that red region, which is considered ionic. Those are ionic bonds, but they have different ionic character. It looks like the highest one we have there is lithium and fluorine. I mentioned that one earlier. Yeah, that makes sense. Actually, a higher should be cesium and fluorine. Is cesium and fluorine in there? Yeah, but oh, okay. Let me see if I can make sense of this one. Lithium and fluorine versus cesium and fluorine. All right. This is 0.7 electronegativity, and that one's 4. Lithium is, I have to go back. What's lithium? Lithium is 1. Sorry. Lithium is 1 and 4. So the difference here is 3, and the difference here is 3.3. We would expect this one to be more ionic. What we have to consider now is the size of the ions. Lithium is extremely small ion, so it can get really close to fluorine, increasing its ionic, the charge separation. Whereas cesium is big, and it spreads that charge over a large atom, a large ion. So that we can't always rely on just the difference between the two. That's why this is sort of a nebulous rule. The size of the ion also makes a difference. Okay. Now here's an operational definition of an ionic compound. I remember when I was working on my PhD, I had a soil chemist on my committee, and I was doing some extractions of soils using different ionic solutions, trying to get at the different fractions of available manganese in the soil for plants. And I would extract it with this weaker substance, and then I get to a stronger one and take out another fraction, a stronger one, take out another fraction. And I asked this, my advisor on my committee, I said, how do I write this up, in my dissertation so that it makes sense? And he says, your procedures are operationally defined, which means they're whatever you want them to be. All right, so the operational definition of an ionic compound is the compound will conduct electricity if the ions are free to move. So if you have a crystal of sodium chloride, and you put a charge here, it's a big, little, big, little, big, little, and you have a light bulb here, and you try to flow a current through that crystal, you get nothing there because those ions are not free to move. So how do we know it's an ionic compound? We have two choices. You either melt it so that sodium and chloride ions can move and complete the circuit, or you dissolve it in water. And in that case, it does confirm that operationally this is an ionic compound. Now, what about ionic solids that don't dissolve? Well, as a matter of fact, ionic compounds always dissolve at least a little bit in water because water is a polar solvent. So you're always going to get a few ions in solution, even though we define them as insoluble. They may be slightly soluble. So you're going to get a little bit of light, even if it's silver chloride. And try to put it in aqueous solution. Not very much goes into solution, but enough goes in so you can detect a current. And we'll talk about that next semester also. Okay. Now we're going to try to describe the chemical bond using models. And a model is an attempt at visualizing what a theory is explaining. So models always accompany a theory. Now there's some things that we have to understand about models. First of all, model is not reality. Like model airplane. A model 747 is not a 747. But it's a representation that helps us visualize where things are. And with a model, if it's properly made, you can change things in the model and see how it affects the operation of the whole system. So if we had a model airplane that was designed to fly, I saw a video of one yesterday. It was, I think it was a World War II bomber, but it had a wingspan of probably about 12 feet. And it was probably about 10 feet long. And it had 2 gasoline engines on it, and it took off. So you can change things in that model and see how it affects its operation. Okay, models are not reality. Models are oversimplifications. And for that reason, oftentimes they're wrong, because when we build a model, whether it's a physical model or a mathematical model in formulas in a computer program, those are models too, you have to minimize certain factors, especially factors you can't control. And sometimes you minimize factors that need to be in there in more prominent places, right? In those cases, your model turns out to be wrong. So as a consequence, models tend to become more complicated over time, trying to make the model fit reality. So when a model goes bad, we have several options. So if your model's bad, you can modify it to make it fit reality better, to predict things about the real world. Or you can restrict its use. Right? You can say, okay, under this set of circumstances, the model doesn't work, so we don't even use it there. Best example is the physical world, right? Isaac Newton's models in his laws of motion fit very well within certain limits, parameters. If it's a certain size, it's not too small, it's not too big, like black holes, then Newton works very well. So we restrict its use. If we have to go to very small, that's quantum mechanics. If we have to go to very big, that's Einstein and relativity. The other thing is to discard it. Start over, right? And that usually happens after you modify it to the point that it's just completely ridiculous. And it makes no sense anymore. And then there's a fourth one that I add. You turn your model into a religion. Right? That's where Darwinism is at. That's where global climate change is at. The people that believe in those things turn it into a religion. Now you're outside the realm of science. All right. If they just read some of Darwin's letters to his friends, they'd find out that what we know now, Darwin wouldn't even agree with his theory. Okay. So there it is. I put it on the board. You can restrict the model's use. You can modify it. Ridiculous. Modify your model so that you're trying to explain. Physicists have been looking for a unified theory. So they combine all the forces in the universe into one theory. The electromagnetic force, the gravity, the strong nuclear force, and the weak nuclear force. And some of their models have gotten so ridiculous, they had to add physical dimensions in the mathematical universe, up to 26 of them, to make them work. The closest that anyone has come to a unified model is the string theory. I don't fully understand it, but there it is. Or you can throw the model out and start over. For instance, the model of the atom, according to J.J. Thomson, was like a plum pudding. Right? You had these electrons that we knew were particles, but the positive charge to balance them was like a pudding surrounding all that. Well, Rutherford came along with his nuclear model of the atom, and he proved that the plum pudding model was wrong. And from that point on, it was dead. He just had to throw it out. Okay. Bond energies. There are conventions in how we deal with bond energies. In order to break a bond, you have to add energy to the bond. So bond energies are reported as positive values, which means endothermic. We have to add energy to the bond. Consequently, if you form the bond, then you're releasing energy, and that's exothermic. And your term will be negative. So when we break bonds, the values are positive. When we form the bonds, values are negative. And we're going to look at a chart in a minute with bond energies, and I'll point out what's the convention for those reference manuals types of charts. How do we represent bonds? Well, a single bond is always 2 electrons between these atoms. That's a single bond. And we typically represent it with a single line. Double bonds then would be 2 pair. And we would represent that with 2 lines. And a triple bond would be 3 pair. And we would represent that with 3 lines. Okay. So that's the convention for representing bonds. Now, I don't know of any quadruple bonds. Triple bonds as high as I've ever seen. Not that they don't exist, it's just I've never seen them. Also characteristic here is as you increase, if you go from single to double to triple for two atoms, generally the bond length shrinks and the bond energy increases. So it takes more energy to break this bond than it does to break that one, than it does to break this one. And this one, the energy, the distance between the nuclei is greater here, shorter here, and even shorter there. Now, the progression from length and energy as you go from one to the other is not linear. It's not linear additive. And I'll explain that later. But this one will not be twice as strong as that one, and this one won't be 3 times as strong as that one. It'll be stronger, but not 3 times, or not double. So here are bond energies. Notice that all those values are positives. What does that tell you? That tells you that the chart is measuring bond energies as how much energy does it take to be added to it to break the bond. That's why they're all positives. Okay, we're breaking those bonds. That's an expression of bond energy. Now, no units are given, but I'm pretty sure those are kilojoules per mole. I'd be willing to bet. Oh, and you can see, for instance, let's see. Okay, carbon-carbon. Carbon-carbon is 347. Single bond of carbon-carbon is 347 kilojoules per mole. Let's say we have a molecule where we have a double bond of carbon. Is 614. Right? That's not double. It's more, it's a lot more, but it's not double. It'll be 694, but it's only 614. And a triple bond for carbon-carbon, and these would have to be in bigger molecules, would be 839. And that's not 3 times this either. And it's not a single plus a double. Right? So that just illustrates that the progression is not linear. Okay. We've already said that. Say it again. Now, if you want to calculate the enthalpy for a chemical reaction, right, the delta H for a chemical reaction, you can take those bond energies and use this formula. So the amount of energy that went in minus the energy that you get back. Well, actually, we put that minus in there because if you get the energy back and the bond energy is in positive units, then that gives you your negative, your energy back. Okay, because all bond energies are positive values in this table, then you need that negative to actually give you the energy back. Okay. And you can measure the enthalpy of a chemical reaction, right, in a calorimeter, and compare it to a calculated energy for the reaction, delta H for the reaction, using this formula, and they're almost exactly the same. So it's a very reliable way of calculating the energy of a reaction. And that's good, because suppose you're dealing with a reaction that you think might be extremely exothermic, even to the point of explosive. It'd be nice to know ahead of time before you try to do the reaction. Okay, so that sigma, I don't know if you've been exposed to this before, in mathematical terms means summation. So you add all those things together for the energy required, and then you subtract all those for the energy released, the bond energies that for the products. When you form the products, first you break everything apart, and the reactants, and then you let them fly back together in their new arrangements. And that's the second part. So it's reactants on the left, products on the right. And if your reaction, say we're doing hydrogen gas plus oxygen gas in a space shuttle engine to make water, it releases a whole lot of energy. Right? So we would need to balance this one would be 2 here and 2 here. Well, whatever the energy for the hydrogen-hydrogen bond here, you'd have to multiply it by 2. Multiply it by 1 here, multiply it by 2 there. And in this case, you would have 2 oxygen-hydrogen bonds. You would have the oxygen-hydrogen bond for this one times 2. Okay. So here's an example for doing delta H of this molecule. So notice the only difference between the 2 molecules, you got a methyl group on the left, CH3. CH3 for both of them. So that didn't change. And the only thing that changed, and you have a nitrogen and a triple bond to a carbon on the right. Right? So it doesn't matter if you have the nitrogen first or the carbon first. The only difference between the two is you have carbon and you have hydrogens here. Then you have this bound to a nitrogen, triple bound to a carbon. And on this side, you have the carbon with those same bonds. This one's bound to the carbon and triple bound nitrogen. So really the only difference is this one. You got the same here, subtracted that one, cancels out. You got the same here, that one cancels out. So all you need is this carbon-nitrogen bond, 305, minus this carbon-carbon bond, which is 347. Right? So that's 242, minus 42 kilojoules for that reaction. Okay? Now you could go all the way through it, I mean, for fun if you wanted. Just add in all the others, but they're going to cancel out anyway. Now, if we had the time, if we didn't have the time, this is where I would stop and pick it up next time. But we have the time, so I'm going to finish. This is about halfway through. Let me erase this thing here. I'll keep that. And we'll keep that. So we have some theories that are operational for bonding. We talked about generalized differences between ionic bonding and covalent bonding. Now we're going to look at covalent bonding in more detail. And sometimes you can expand this into ionic, but let's stick to covalent for now. I think it's easier to understand. The theory, the overall theory, and this is in chronological order. This theory came out of, probably came out of Pauling's work, the valence bond theory. I'm just thinking for just a second. Okay. The valence bond theory. Okay, what's in a name? Well, it's a theory. And talking about bonding, it's talking about bonding in terms of valence electrons only. You don't have to consider the core electrons for this bonding theory. Okay. What it says is that the bond is formed by the overlap of atomic orbitals. Okay, so two atoms come together, the simplest would be two hydrogens. Two hydrogens with their 1s orbitals, right? One electron each. And we get an overlap between those 1s orbitals. And they share an electron from each one. That forms your covalent bond between the two hydrogens. That sharing of electrons through overlapping orbitals is key to the valence bond theory. Now, let's emphasize the fact that these orbitals are overlapping. We get the overlap, those orbitals, those 1s orbitals. But those 1s orbitals still belong to each atom. They can reclaim them anytime. I'd have to dig into my haversack and get another marker. Now, there's a model that goes along with this called the localized electron model. And it basically says that any molecule where you have atoms bonded together, they are bonded by sharing of pairs of electrons. So in this case, we only shared one pair of electrons. But if you have two oxygens together, you can share two pairs of electrons. Right? These are shared electrons. These are lone pairs or unshared electrons out here. When we say localized, we're emphasizing the fact that these electrons still belong to the atoms that they came into the party with. Okay. And I know I'm hammering that concept because when we get into chapter 9, we're going to get into the quantum mechanical model. And in that model, all bets are off. Once you form the molecule, those electrons belong to the collective. You know, it's like molecular communism. So we got the lone pairs out here, and then we got the bonding pairs here. All right, so we're going to look at part 1 and 2 in this chapter, in chapter 8. Yeah, chapter 8. And then we're going to hold part 3 for chapter 9. So that'll come in the next exam. You don't have to worry about that one right now. We'll just master part 1 and part 2. Okay. Oh, we didn't do Lewis structures yet, did we? We haven't done Lewis structures. Okay. I'm introducing you to stuff we haven't studied yet. That was earlier in our lecture today. Okay, so G.N. Lewis was an American chemist, and he was also brilliant. But he developed this system for simplifying the modeling of compounds based upon their valence electrons. So he said, here's the symbol, right? The element symbol, whatever it happens to be. And he was basing his reactions upon the octet rule. He said, what this atom wants to do when it bonds is to end up with 8 electrons around it. And he represented them by pair here, and here. Right? Now, if it was like fluorine, right? If that were fluorine, it would only have 7 electrons. Right? And the easiest way to tell is to count from the left. 1, 2, 3, 4, 5, 6, 7. 7 valence electrons. And if we had, which we don't on this chart, we had the old style Roman numerals. There'd be a Roman numeral 1, 2 over the alkali metals and alkaline earths, and then start with boron would be Roman numeral 3, 4, 5, 6, 7. Roman numeral 7 would tell you have 7 valence electrons. That's the advantage of the old system. If we went to oxygen, it would be 1 to the left. So oxygen would have a pair here, and 2 lone pairs like that. Okay. What Lewis was getting at is when they come together, by sharing electrons, they convince their neighbors that they now have octets. So if we took fluorine and hydrogen together, right? Hydrogen, I'm going to say hydrogen has its 1. There's hydrogen's electron. Then if we shared these 2 like that, we would have fluorine, hydrogen, and then fluorine would have these. Fluorine, okay, we're going to anthropomorphize again. Fluorine thinks it has 8. 2, 4, 6, 8. Whereas hydrogen needs the duet. So it thinks it has 2. So that's the whole premise behind Lewis structures and the way they combine to make compounds. And it's still useful today. There's what the duet rule would be for hydrogen. It's trying to look like helium. And fluorine is the octet rule. If we put 2 fluorines together, and actually, if I'm consistent, I need X's here, don't I? Then we combine these 2. Now the fluorine on either side thinks it has an octet. Now, we didn't create or destroy electrons, but by sharing, now they've convinced each other that they both have octets. All right, single bonds, double bonds, triple bonds. Steps for writing the Lewis structure. Now, are you sure we didn't do Lewis dot structures for individual elements? I guess not. I'm sorry. Can't be helped. But if you have a molecule of any size, you can write a Lewis structure for it. Say we have, let me see if I can figure something that's complicated but not too complicated. How about okay. How about methanol? CH3OH. That's methanol. Wood alcohol. You know, the kind that makes you go blind if you drink it. The one that you want your moonshiner to get out of there before he catches the ethanol. Okay, so we want to draw the Lewis dot structure for this one, recognizing that when we write it this way, those hydrogens belong to this carbon, and there's a carbon attached to that oxygen. That's the way organic compounds are written. So it would be like this. Like that. Okay. So in order to write the Lewis structure for that, and I've already written part of it for you, we look at the valence electrons for each atom. So carbon is position 4 from the left. It has 4 valence electrons. 4. And we have 1 each for these. And oxygen has 6. Right? So 3 plus 1 is 4 for the hydrogens, 4 for the carbon, and 6 for the oxygen. We have 14 valence electrons that have to be positioned in this molecule. First thing you do is you be sure you have the basic structure and arrangement of the atoms in this case, and you put 1 bond for each one. Okay. And then you count up 2, 4, 6, 8, 10 pair, 10 electrons, 5 pair. And you subtract those. We've already used those up. We only have 4 electrons left. Then you start from the outside and work your way in. Right? Hydrogen can't take anymore. Right? It's only a duet. Carbon's already got 2, 4, 6, 8. Right? So the only place that these 4 electrons can go is on the oxygen. So we put a pair here and a pair here. That's your Lewis dot structure.
Our example here is for water. It's a little simpler. Right? We have a total of 8 electrons, 2 hydrogens and 1 oxygen, 8 valence electrons. Right? This is the valence bond theory. Now, that's what it would look like. Wait a minute. There we go. That's what water would look like without the knowledge of geometry. We don't have any knowledge of geometry yet. Right? That takes another model, the VSEPR, which fits under the valence bond theory. So we have this localized electron model. We also have the valence shell electron pair repulsion model that goes with it. And that gives us an idea about geometry. Okay. Phosphorus tribromide would be that. Hydrogen cyanide would be that. And we go through the same procedure as before. We've got single bonds, and then we have, well, let's do the hydrogen cyanide. That was a fun one. So we know our molecule is like this. So that's 1, 4, and 5, correct? So that's 10 electrons. Okay, so we put a single bond here, here, and here. That's -4, right? 2 pairs. 6 electrons. So where do those electrons go? Work from the outside in until we've used them up. Well, 6 electrons could go right here, like that. But that doesn't give carbon an octet. So how do you give carbon an octet without stealing the octet from nitrogen? You share. Take these 2 electrons, make another bond. Take these 2 electrons, make another bond. Now we have 2 for hydrogen, 2, 4, 6, 8 for carbon, 2, 4, 6, 8 for nitrogen. Okay. Those are Lewis structures. Let's see. Hydrogen's easy, too easy. How about ammonia? Let's do ammonia. Because we're going to see ammonia again. Quite often, actually. So nitrogen has 5 valence electrons. And then we have 1 each for hydrogen, which is 3. So we have 8 electrons. So we put, we have to decide which one goes in the middle. Right? And nitrogen has to go in the middle here because hydrogen can only handle 2 electrons. So we have to put nitrogen in the middle. There's no other choice. Then we put a single bond for each of the hydrogens. That's -6. We have 2 electrons left over. Hydrogen can't take any more, so we put that lone pair on nitrogen. Now, exceptions to the octet rule. This is based upon the fact that these compounds I'm going to show you are real. We know them. We know the ratio, the mole ratio, in this case, boron to hydrogen is 1:3. That's established for that compound. So we got to make our theory fit if we can. Well, boron trihydride has 6 electrons. But if you put it together like that, we use them all up. There's no octet for boron. So this is known as an octet deficient molecule. But it's real. Okay? And you'll find those usually with boron and smaller, like boron, beryllium, and lithium are notorious for forming incomplete octets. We can go the other direction where we exceed the octet. This one's a little easier to explain. For instance, if we have sulfur tetrafluoride, that has 34 electrons. Well, if we put sulfur here and 4 fluorines, oops, That's 2, 4, 6, 8 minus 8, which is 26 electrons, right? So 2, 4, 6, 8, 10, 12. Usually you circle and put 1 each until you get your octet, but I know what the outcome is going to be. So I have 4 times 6 is 24. I have 2 electrons left over. They have to go here because those octets are already full. So sulfur exceeds the octet. 2, 4, 6, 8, 10. Has 10 electrons. Okay, how do we account for that? Look where sulfur is located. Right here. In the third period, if N equals 3, what can L equal? 0, 1, and 2. S, P, and D. There you go. You have available 3D orbitals for those 2 electrons to go into. All right, so the third period and higher will typically produce exceeds of the octet because they have the d orbitals available. The next one, arsenic pentabromide, is a similar situation, only there all those electrons are bonding. So he has 10 bonding electrons, whereas sulfur had 4 pairs of bonding electrons and 1 pair of non-bonding. Okay, so boron trifluoride, since fluorine has available space, hydrogen didn't have space, fluorine does, and we can satisfy the octet for bromine with fluorine. And then phosphorus trichloride, pentachloride, that exceeds the octet. And sulfur hexafluoride also exceeds the octet by quite a bit, 12 electrons. Okay, what I may do is introduce this topic now. I've got a slide on it, but stream of consciousness. Notice that boron trifluoride like this. 2, 4, 6, 8. And the fluorine here. Who's to say that it's that fluorine that gets the double bond? Nobody. We could have put the double bond down here. And put a single bond up here. Right? Well, who's to say that that was correct? What if we did the double bond on this side? Each one of those is a valid Lewis dot structure, right? So how do we deal with it? This is one of the problems with the localized electron model, right? You can't decide because the electrons have to belong to individual atoms. We can't split them up, right? So this is a possibility, that one's possible, that one's possible. And I'm going to show you later, the solution to that is called resonance. We just say, they're all possible. So this thing resonates among all 3. So here we're getting into the modification of models to satisfy reality. Okay. This is just a review. Carbon, nitrogen, oxygen, and fluorine should always be assumed to obey the octet rule. They're not going to be deficient or they're not going to exceed octet. Beryllium and boron, they typically, they can be deficient. It depends on what they're bound to. Second row elements never exceed the octet. Sometimes they're deficient, but they never exceed. Third row elements, which have access to 3D orbitals, can exceed. They don't always, but they can exceed the octet. whenever possible, satisfy the octet.
But be ready to either be deficient or exceed, and be prepared to explain to back up your choice. All right. So here's another example. The nitrate polyatomic ion. And notice when we drew the structure for that one, we have to put the negative sign in. If you don't have a negative sign, then you're shorting an electron. That negative sign is an electron that must be added. So if you have nitrogen is 5 and 3 times oxygen, which would be 18, that would only be 23 electrons. But you've got a negative charge, so it's actually 24 electrons. So if you draw the nitrate like that, without the negative, it's wrong. But we can put the double bond in 3 different locations, just like we did here, and that's resonance. That's Linus Pauling's solution to this problem with that model. He introduced the concept of resonance. So it's not any one of these is correct. They're all correct. And it happens at such a fast rate, they resonate. Now, I've seen it done this way, where we just take all of them and say, they each bond has partial single and partial double bond character. And this is actually closer to reality because we can measure the bond length. These bond lengths are all the same, exactly the same. We would expect this one to be shorter than these two, but it's not. So this is closer to reality, but it doesn't fit the model because the 2 electrons that are in here have been spread out. They don't belong to that one anymore. And we can't do that with that model. It's localized. So we're kind of, we painted ourselves into a corner with this theory. This delocalization is actually a good thing. If we can delocalize those electrons like this, that stabilizes the molecule. When you can spread those electrons out further into more area, it brings their energy down and stabilizes the molecule. Okay. Let's see. Do I want to do, we've already done methanol, carbon dioxide. Let's see. I'm going to skip those. You'll get enough practice drawing those with the review document. So in the interest of time, I'm going to skip to the next topic. Now, I mentioned the term valid Lewis dot structure. How do we know one is valid and one's not? Because this is just a series of steps that you use to draw the structure. And in some cases, the sky's the limit. You can draw a whole bunch of different structures. What we want to do is settle on the most likely structures that we call valid Lewis structures. And if we have several structures and they're not, we can't rationalize their equivalence like we could with the nitrate ion, right? Those all look the same because all you have to do is rotate one and it looks like the other one. But if we have different Lewis dot structures proposed, how do we know which one is the best? And that's where the concept of formal charge comes in. This is like a bookkeeping scheme that we use, like I'll think of it just a second. Maybe not. Wait a minute. Have we even got to No, I don't think we have. All right. So never mind. We'll get to it later. Formal charge is a bookkeeping scheme for tracking where electrons are located in a molecule. It's not really a charge because these are covalent molecules. These are covalent bonds, so you don't have charges. But the formal charge is a way of accounting for valence electrons and giving us an idea of what is the most stable arrangement. Okay, so when we calculate formal charges for each of the atoms, and I'll show you how to do that in just a minute, we calculate those formal charges. We want the collection of formal charges that are all or each as close to zero as possible. Also, if we have to put a negative charge, a formal charge in there somewhere, it's going to reside on the most electronegative atom. So if we had boron and fluorine in there and had a charge, formal charge on it, formal charge would be on the fluorine. The negative would be on the fluorine. Okay, so how do we calculate formal charge? Well, if we have a molecule, let's say, let's take a simple one like water. So we got a pair there, non-bonding pairs and two bonding pairs. We would calculate a formal charge for each one of these atoms. We would take the number of valence electrons for the free neutral atom. So oxygen would be 6. 6 valence electrons for oxygen. Then we would add up the electrons that are assigned to it. Lone pairs belong exclusively to that atom. So that's 2, 4. Bonding electrons split in half. So it'd be 2, 4, 5, 6. Minus 6 equals 0. So the formal charge on oxygen in this molecule is 0. Valence electrons for hydrogen, well, 1, right? 1 each. So how many do they get? Well, they don't have any lone pairs, but they've got 1 from that bond. That's good. They're all 0 formal charge. Okay. Let's see. Let's do this example. Let's see. That's the chlorate, phosphorus chlorate. Actually, I think the name is a bit different. But for this molecule, and they've given us the Lewis structure, so we don't have to mess around with it. I'm gonna have to get another marker. These things don't last very long. I mean, they still mark, but they fade out too much. I want a nice black line. So if we draw this compound, chlorine, yep, chlorine, and oxygen. That's the way they drew it. And each one has an octet. That's what we'd get if we drew the Lewis dot structure from that POCl3. Now we want to do formal charge. Well, let's do the chlorines because there are 3 of them. We'll get those out of the way. Chlorine has 7 valence electrons, right? So how many has it got? 2, 4, 6, and 1 from the bond is 7. So each one is 0 because they each have the same arrangement. How about the oxygen? Well, the oxygen is 6 minus what? 2, 4, 6, 7. That's a minus 1. Phosphorus is 5. Yeah. Phosphorus is 5 minus what? 1, 2, 3, 4 equals a plus 1. So I can't think of any other structure that would give us a different formal charge. So we have to go with this one. So oxygen is minus 1 and phosphorus is a plus 1.
Now, which one's more electronegative? Well, oxygen is up and to the right, which makes it more electronegative. So it would have the negative charge, and that's what we calculated. That's where it should be. Now, we don't have any competing structures for that, so we go with this one. But notice that all the formal charges must add up to 0. 0, 0, 0, plus 1, minus 1, 0. Or if it's a polyatomic ion, the formal charges have to add up to the charge on the ion. So if we did this for NO3 minus, all the formal charges would have to add up to a minus 1. Okay, there's our calculations. All right. So here's an example of two non-equivalent Lewis dot structures. If we drew these for carbon dioxide. So let's show how they came to that conclusion. That's 4 valence electrons, and this is 6 times 2. So that's 12, 16, right? 16 electrons. Yeah. So if we drew them like this, that's minus 4 would be 12. 2, 4, 6, 8, 10, 12. Okay. So how are we going to make an octet for carbon? We have two choices. Right? We can take these two here, do that. And that would give carbon an octet. Or we can do this. Take one from this side and take one from the other side. Okay. So those are non-equivalent Lewis structures. They're not the same. There's no way we can arrange this one to make it look like that one. So the way you decide which one is preferred is you calculate the formal charge. So this is 4 minus 1, 2, 3, 4 equals 0. And this is 6 minus 1, 2, 3, 4, 5, 6, 0. So this is a 0, this is a 0, and that's a 0. I mean, it's a no-brainer, actually. But I'll do this one anyway. If this is 6 minus 2, 4, 6, 7 is a minus 1, this is still going to be 0, right? 4 minus 4. And this is going to be 6 minus 1, 2, 3, 4, 5 equals a plus 1. So there you have a plus 1 minus 1 as opposed to a 0, 0, 0. This is the best one. And actually, experimental data proves that this is the correct one because those bond lengths are exactly the same, whereas this one would be shorter on that side, longer on this side. So we know physical evidence is that this one is the best one too. All right. Right. This just emphasizes the point. These are not actual charges. This is a bookkeeping scheme for electrons. All right. Now, I mentioned this model, the EXAMPR model. This is the valence shell electron pair repulsion model, the EXAMPR. What that means, and this gives us a handle on the geometry of the molecule. Because what it says is, once you've got your Lewis dot structure, you can use it to keep the electrons separated as far apart from each other as possible. So if we had something like this one, carbon tetrachloride, and we do the Lewis structure, we would have 4 chlorines around here. And each would have its octet. Right? What would be the most stable
geometric structure of that molecule that would keep those chlorines as far apart from each other. And actually, the bonding is what we're talking about. Valence shell electron pair. This is the electron pairs. Keep those as far apart from each other as possible would be the regular tetrahedron. So we would draw, say, a tetrahedron. We'd have carbon in the middle, and we'd have a chlorine up here, chlorine down here, and a chlorine in the back. So this would form the triangular base here, and then connect these to the top would give you the triangular pyramid shape with the carbon in the middle. That's your tetrahedron. So whenever you have 4 electron pairs, the most stable format is the tetrahedron. Okay, this is a geometry predicting model. We try to maximize the distance between the electron pairs in the bonds themselves. Now, for large molecules, you can have several different geometries. Like you have a big molecule, you might have a tetrahedron over here, you might have a linear here, and you might have a trigonal planar over here. So you can mix them up in big molecules, but we're going to try to stick with small molecules, smallish molecules, and try to focus on these individual shapes. Okay, this molecular structure, linear model, okay, has I'm gonna have to erase this now. When we talk about bond angles, we're talking about whatever the central atom is. And we need 3 atoms to form the angle. So the angle here, the way we present it here, it looks like 90 degrees, doesn't it? But it's not, because the bond angle here is between that, and that, this. So that angle for a tetrahedron is 109.5 degrees. That's the only one you have to memorize. The rest of them you can deduce. For a linear molecule like carbon dioxide, the bond angle is 180 degrees. That's the only possibility. For a trigonal planar molecule like boron trihydride, boron in the middle, hydrogens here, here, and here. That bond angle would be, right, if we're going to go 360 degrees, 3 into 360 is 120, right? So this bond angle is 120 degrees. That's a trigonal planar. And I showed the tetrahedral already. All right, there are 2 more we're going to cover in just a second. Trigonal planar, tetrahedral. Oh, not going to show us the other ones? This is a case where you have 3 equally spaced bonding pairs. This one has 2. This one has 4 pairs, or it can also be groups. And I'll explain that in just a minute. What if we have 5 pairs or groups? Well, in that case, you need a trigonal central with your central atom, and then you need 1 up here and 1 down here. So this is a trigonal bipyramid. It's like 2 tetrahedrons stacked together, only they share the base. So we got a position for 5 here, 3 around the triangle, and then 2 apex. And then the last one we're going to do has 6 pairs or groups. And this is octahedral. Right? Whenever you see hedron in the name of a shape, it's 3-dimensional. In this case, we have a square in the center with whatever the central atom is. And then we have one down here. So we got a position for 4 here and 2 there and 6 pair. And if you do the connections between all the positions on the outside, you find 1, 2, 3, 4 on top, 4 on the bottom. That's octahedral. Okay. So when we're using the VSEPR model, the first thing you do is draw the Lewis structure. Then you count the number of electron pairs or groups. The reason I say groups is because double bonds and triple bonds are treated like one. So this has 2 groups. Or if you had this one, right, like we showed before. Right, that would have 1, 2, 3 groups. And this would be trigonal planar because there are no lone pairs. When you do this, I mentioned here, I talked about it as if every position was occupied by an atom, but it doesn't have to be. It could be a non-bonding pair of electrons. So if you have a non-bonding pair of electrons, say at the apex here, and the rest of them are occupied by atoms, now what do you have? Well, you have that X in the middle, but you've got a square pyramid. Let's put it down here. Be easier to understand. Put it down here. Then you've got atom here, 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 and here. That's a pyramid of Giza. Okay. So you get 2 types of shapes. You get electronic shape, where you count all the lone pairs and the bonding groups. And you get the electronic shape and the molecular shape. That's where you discount the lone pairs and look at the shape that's left behind. For instance, ammonia. Ammonia is like this. Right? 4 pairs. So electronically, it would be a tetrahedron. But once you put it into that tetrahedron, if now you put nitrogen in here, and a hydrogen here, and a hydrogen in the back, and a lone pair up here, what do you have? You have a trigonal pyramid. Okay. So there's a difference between the electronic structure and the molecular structure that we'll describe in more detail in just a minute. Here's the examples. So this one's linear, the hydrogen cyanide we drew before. It had a triple bond on one side and a single on the other. That's 2 groups. It's linear with 180 degrees bond angle. pH3 is like ammonia. It's going to form a trigonal pyramid with nominal bond angles of 109.5. But the thing about non-bonding electrons is if they're not confined in a bond, they tend to balloon. And that adds pressure on the others. So it changes these bonds. Now this bond, there's not a bond there. But there's a bond here, right? A bond between here, here, and here. And that bond is no longer 109.5, but it's been squeezed. So it's closer to 107. Okay? But we start at 109.5 and then we modify it according to the circumstances. For water, water would have right? Electronically, it's a tetrahedron, right? Because it has 4. 1, 2, 3, 4. But when you cover these up, what's left? It's a bent molecule. That's it. And this bond is less than 109.5 because now you've got 2 lone pairs putting pressure on those bonds. O3, that's ozone. It's also built like water. So it has three possibilities. It has this one, this one, this one, like that, that. No, just one. And this, right? So this central atom forms a trigonal planar. But when we cover up that lone pair, it's bent. And sometimes you'll see angular rather than bent. Krypton tetrafluoride has, we draw the Lewis structure for krypton tetrafluoride. There's your 4 fluorines. And each one has an octet. But we have 2 extra pairs. So that would be octahedral. Right? 1, 2, 3, 4 bonding and 2 non-bonding is 6. So that makes octahedral, electronic. So that begs the question, where do the lone pairs go? Well, in an octahedral arrangement, the lone pairs go on the apex. They're the least interfering at that position. That means the fluorines are on the square. So the molecular structure is square planar. Okay, a molecule that has polar bonds will always be polar. True or false? False. Correct. Why? Because we have to consider the geometry. All right. CO2, is it polar or non-polar? Well, we draw the molecule. Oh, we did that already. Draw the molecule, it's linear. You have dipole moments equal and opposite in a linear molecule. So that gives you cancellation of the polarity, and CO2 is a non-polar molecule. Okay, Lewis structure for xenon tetrafluoride. Does it contain lone pairs? Well, yeah. It's like this one. Krypton tetrafluoride, xenon tetrafluoride, you got the same situation. It has lone pairs, but even though fluorine is extremely electronegative, you got each one pulling right on that square planar, right? 90 degrees to each other. They cancel each other out. That molecule is nonpolar. Okay, here's our list. So we got linear trigonal planar with 3 electron pairs. Usually what I do is create a table up here with examples. So let's see, electron pairs or groups. So the linear has 2. Trigonal planar has 3. Tetrahedral has 4. Trigonal bipyramid is 5, and octahedral is 6. Oh, I did that over here, didn't I? Okay. But there are physical models for you to look at. Okay. These are cases where every position is occupied by an atom. So in this case, the electronic structure and the molecular structure are the same. But here's a case where you have a tetrahedron and you have 1 lone pair. This is like ammonia. This is a trigonal pyramid. Or if you have 2 missing, you've got a V shape, an angular, or a bent. You see all 4 all three different names. I like bent. It just sounds cooler. Here's a case where you have a trigonal bipyramid. And in the top one, of course, every position is occupied by an atom. But what if you've got one lone pair? Where does it go? It turns out, and this is supported by physical evidence, the lone pair goes on the triangle. See where it's on the right of that triangle? So when you look at the molecular structure, you get a seesaw. You just turn that on its side. You got the two struts here, and then the seesaw. If you have another lone pair, it also goes on the triangle in the center. So that leaves you with a T-shaped molecule. And of course, if you have three, all three go on the triangle. Now you have a linear molecule. Now that's as opposed to octahedral. When we do octahedrals with the lone pairs tend to settle on the apex of the pyramids. Okay. Are we getting close? We're closer to the end than I thought we were. Okay, so make some room here. I have a feeling I'm going to need it. Yeah, let's erase this one and this one. Everything's under the valence bond theory. Okay. When phosphorus reacts with chlorine gas, the compound phosphorus pentachloride is formed. In the gaseous and liquid states, this substance consists of PCl5. But in the solid state, we get a rearrangement where you get a combination, a 1-to-1 ratio of PCl4 plus and PCl6 minus ions. And those are the ones that cation anion arrangement puts them into a lattice where the PCl4 plus is one geometric structure. It's derived from PCl5, which is another structure, and it's combined with PCl6 minus in its lattice. So we got three structures there to deal with. The PCl5, of course, is a single structure for the gas and the liquid. But the solid is composed of a combination of the PCl4 plus and the PCl6 minus. So what are those structures? Well, PCl5, we start with that one. That's a trigonal bipyramid. So we would say PCl5 and phosphorus is 5, chlorine 7, 35, that's 40 electrons. Right? So we have 1, 2, 3, 4, 5. Chlorine, 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 chlorine. And that's 2, 4, 6, 8, 10. Minus 10 equals 30. 30 electrons. So if we put 6 around each of the chlorines to complete their octets, 6 times 5 is 30. We've used them all up. So this is a trigonal bipyramid. Okay. If it goes into the solid now, we have a PCl4 plus. Right? Okay, so how many do we have here? We have 5 there. 7 times 4 is 28 minus 1 because that's a positive charge. So that's 32 electrons. Okay, so if we do that one, Cl, 2, 4, 6, 8, which is 24. 2, 4, 6. 6, 6, 2, 4, 6. 6 times 4 is 24. We used them all up. But this structure has a positive charge, and that means it's tetrahedral.
Okay. The last one, PCl6 minus. So we still have 5 here, and we have 7 times 6 is 42, right? Plus 1. So that's 48 electrons, right? So we have P, 2, 3, 4, 5, 6. Okay? It's 2, 4, 6, 8, 10, 12. Minus 12 is 36, correct? 2, 4, 6. 6 around each chlorine gives us the octet for chlorines. That uses those up. And this is negative charge. So 6 groups is octahedral. Okay. So in the gaseous and the liquid states, we have trigonal bipyramid. In the solid state, we have a combination of 1-to-1 ratio of tetrahedral and octahedrals, cations and anions. And the overall ratio of phosphorus to chlorine is the same as this one, if it's 1-to-1. Because this, if we multiply this by 2, we get 2 phosphorus and 10 chlorines. 2 phosphorus and 10 chlorines. So we haven't created or destroyed any atoms in the process. Okay, so that's what the trigonal bipyramid looks like in the gas and the liquid state. The PCl4 plus gives you the tetrahedral, and the PCl6 minus gives you the octahedral. Let's see. All right. We don't expect noble gases to be reactive, but they can be forced, especially for the larger ones, like xenon and krypton. Xenon is probably a better candidate. The bigger the molecule, the more diffuse the electron density, and the easier it is to form bonds. So we can force those bonds. Let's see. Did I miss anybody? Henshaw. No, Henshaw. Okay. Right. Okay. But in the 1960s, krypton, xenon, and radon were synthesized with compounds. Probably some graduate student who was trying to work his way through a PhD degree. Got saddled with this project and came out with it. Says, okay. And so I can imagine the student walking into his major professor's office and saying, I did it. and the professor's eyes go like this, and he says, ooh, I can get at least 6 papers out of this one. Okay. So xenon tetrafluoride was one of those compounds. Predict the structure, and does it have a dipole moment? Right. I think we did xenon tetrafluoride before, and it turned out to be square planar. Right. It's got 2 lone pairs, but those lone pairs are located at the apexes of the pyramids on that structure. So that means all the fluorines are in the square. And that also means that their dipole moments cancel. So they're equally spaced around that square. Now, this is a possibility. I mean, if we put the lone pairs on the square, we get a seesaw. Well, the other possibility is putting the lone pairs on the apexes, and we get a square planar. The way to break the tie is to ask yourself, which one is polar? The one on the left is polar. It has unbalanced dipole moments, whereas on the right, we have balance. So all you have to do is test it for polarity, and that settles the argument. And it turns out that that molecule is nonpolar, right? So that means the structure has to be square planar.
Okay. That's nothing new. That just settles the argument. Okay. Okay, that's it. We're done with chapter 8. And next Tuesday, because I won't be here Thursday, next Tuesday we'll do a review on this. And like I said before, if you want to jump ahead, there's a review in there of a previous semester. Otherwise, we'll come back on Tuesday and review this information. And that means Thursday will be the exam. So you may want to use the review resources in Brightspace. Otherwise, you'll only have 2 days after the class review to get ready for the exam, and that may not be enough. But practice drawing these things. It gets easier with time, like anything, like balancing equations or other types of calculations. It gets easier the more of them you do.